Hi everybody, Mr. Rubo here. Today we are starting 311, which is secant, cosecant, and cotangent functions. So those three things are what we call the reciprocal functions. The reason they're called reciprocal functions is because they are the reciprocals of the basic three. So secant is the reciprocal of cosine, cosecant is the reciprocal of sine, and you'll never guess, cotangent is the reciprocal of tangent, which if you recall, tangent was also the sine over cosine, um, which means you could rewrite cotangent also as cosine over sine, right? That's right, reciprocal meaning just flip the fraction. For these guys, in all these cases, the denominator cannot equal 0, right? Because we don't want fractions to have 0. So you'll see, hey, the graphs of these reciprocal functions will include vertical asymptotes whenever the denominator is 0. So the easiest way to find those is graphically. So here you'll notice I want to graph secant x, and if you notice what graph that is here in dashed lines is the cosine graph. And specifically, you'll see these what we would call key points. We have the maximum, the midline, the minimum, and then back to midline, maximum, right? These points are the key points. And not only are they key points for cosine, they are very key points for secant. The reason why is because they will give us all our big points. So whenever cosine is 0, which we can clearly see from this graph, there's this point right here, there's this point right here, there is this point right here, and this point right here. So if I start listing those out, 3 pi over 2, I'm sorry, negative 3 pi over 2, negative pi over 2, pi over 2, and then 3 pi over 2. Well, this is only just part of the cosine graph or part of the secant graph. This does keep going forever. So there's dots and dots in both directions, but all of those points are where we would have vertical asymptotes. All right, and then you may be like, okay, well, what happens in the middle between those? Well, reciprocals, when you think about what they mean, well, let's start with this other these maximum and minimum points. What is the reciprocal of 1? Hopefully you said 1, because it is. So this point is the same whether we're talking secant or cosecant. Well, now we're starting in the cosine graph. We're going down, which means we're getting like fractions, right? So like 1/2 is one possible answer. Well, when you do the reciprocal of that, you get 2. When you reciprocal these smaller fractions, you actually get bigger numbers. So what ends up happening is this like U shape that's between these vertical asymptotes actually gets flipped upside down, and it's an upward facing U. Well, same thing happens in this section here, except we're down here, -1, reciprocal is -1, and then we're flipping all these fractions, but they're still negative, so they get bigger negative numbers. So then it's a U facing down, and that's what happens in all these sections, is either it's a U facing up or a U facing down. So that is the graph of secant based on cosine. But the kind of key things here, we have the vertical asymptotes here. And the really nice thing, if the pattern that occurs here, is that our verticals are always at the lines x equals, and you could technically choose any one of these. I'm going to choose the first positive, so I'm going to say pi halves. And then you'll notice all of these are pi apart. So you would say plus pi k, where k is an integer. Okay. So there is where all of your vertical asymptotes are. And then your domain, well, because these are vertical asymptotes, that's basically how you're going to find your domain. It's where x is not equal to these things, right? So you end up writing almost the exact same thing. If asked about the domain, you just throw a not equal sign in there, right? I've got a little set notation here. You don't technically need the full set notation. You don't have to have this X bar and then the squiggle. You could just write that. This is more proper, but you know, it is what it is. So yeah, we actually end up doing the exact same thing with cosecant, but the only difference is we draw a sine function first. So now we're looking at all the zeros of sine, right? So it's all these guys. Those are where our vertical asymptotes are. And then kind of same idea, these top maximums are where our U's centers are, and then we just flip, and here is our graph. So, and just to point this out with both of these, those dashed lines are not part of the graph. They're guidelines, right? So if we look here, it has vertical asymptotes. If you look at the pattern, you got one at negative 2 pi, one at negative pi, you have one at 0, you have one at pi, you have one at 2 pi. So here you could actually say it's at any of these. So why not just say x equals 0 plus pi k, where k is an integer. And my pen stopped working again. There we go. Where k is an integer. Okay. And guess what? Domain, written the same idea, x not equal to, and you can say 0 plus pi k, where k is an integer. And technically, we can drop the 0 if we wanted to and just say x equals pi k. That would also be 100% accepted, right? Adding 0 doesn't do anything. So now if we look at the ranges of both of these, you'll see they are very similar, just how the ranges of sine and cosine are the same. The ranges of secant and cosecant are the same. They have a gap where sine and cosine would be. So if I look at the lowest value is negative infinity in both cases. They go all the way up to negative 1, and they include negative 1. But then there's nothing in between negative 1 and 1. So then we've got a big old gap, and then we say, okay, it starts up again at 1, and then all of these graphs go up to infinity. So we throw that infinity symbol. And remember, infinities are always parentheses. All right, and then last thing for this video is the general form. You've seen this before with sine and cosines. Well, cosecant and secant, it's almost exactly the same. So period is still 2 pi over b, and period's always positive, so we just throw absolute value there. The absolute value of a is the vertical dilation. Right, we can't really call it an amplitude change. It kind of is, but it kind of isn't. And then if a is negative, then it's a reflection, right? Reflection in the x-axis, right? And then c, well, negative c is our phase shift, right? The opposite of c is phase shift. And then d is the midline, or vertical translation. And all of that's basically the same as it is for sine and cosine. You would treat it the exact same thing as a sine or cosine graph, but then you just draw those vertical asymptotes in and then make the u's. Okay. So that's it for today's video. Thanks for watching. Have a good day.